Yesterday we talked about weak acids and weak bases and how we're going to use ice tables to calculate the pHs of solutions um, for those. But we also indicated that salts can act as either acids or bases, or at least change the acidity of the solution to make it more acidic or basic. And this is the idea behind the Bronsted-Lowry concept of acid-base reactions, basically treating them as proton transfer reactions. So for example, when we throw a solution of sodium cyanide into water, we know that the sodium cyanide is a strong electrolyte because rule number 1 says that any salt that contains the group 1A metal, such as sodium or the ammonium ion, NH4+, is a strong electrolyte. It's a soluble salt and completely dissociates into its individual ions. Now, a 0.1 molar solution of sodium cyanide actually has a pH of 11.1, so it's fairly basic. But we wouldn't recognize sodium cyanide as being either an acid or a base. In fact, we would classify it as a salt. But this salt is obviously acting as a base since it is increasing the pH above a pH of 7. So what do we have? So again, we have the sodium cyanide. We know it's a strong electrolyte. It's a soluble salt. So when we throw it in water, it's dissociating into the sodium ion and the cyanide ion. But these ions can actually hydrolyze, okay? And hydrolyze is just a fancy word for saying can react with water. And so, for example, for the sodium ion, when it's in water, when the sodium ion's in water, it might not be obvious at first what's happening here, but remember, water does self-ionization. And so basically, it's an equilibrium with the H plus and the OH minus. Now, we don't normally think of water as being ionic, but a lot of times it's helpful to think of water as being ionic. Okay, again, it is not. Remember, it has an equilibrium constant of 10 to the negative 14, which means there's almost very little of this ionization going on, but it does exist. And so the cation could react with the anion, in this case, the hydroxide, and basically what it would form would be sodium hydroxide and the hydrogen ion. But looking at this, we know that sodium hydroxide is a strong base, and a strong base always dissociates. So the reality is it's never going to go in this direction, because as soon as it would form this, it would immediately go back and dissociate into the sodium and the water. So you're going to hear me talk about the cations of strong bases not hydrolyzing. This is what I mean. So when I say the cation of a strong base will not hydrolyze, basically it means that nothing's going to happen. It's going to remain as just the sodium ion by itself in water. The cyanide ion, on the other hand, when it reacts with water, well, it's going to be a proton transfer reaction. A hydrogen ion is going to be transferred to the cyanide, right, since it's going to be the proton acceptor, and it's going to form hydrocyanic acid and the hydroxide ion. Now, in this case, the hydrocyanic acid is a weak acid. Since it's a weak acid, we will have equilibrium. So when the cyanide ion is present, we have all of these species in solution, right? Again, it's a weak electrolyte, so it's going to be in equilibrium. So we would actually classify then the cyanide ion as a Bronsted-Lowry base. So we can see then that the hydroxide ion is the product. So in other words, we're increasing the hydroxide ion concentration, which means it's going to have a pH that's greater than 7, and thus explains why a solution of sodium cyanide would be basic. So again, we see that the cyanide ion itself reacts with water to produce the hydrocyanic acid and the hydroxide ion. Again, we call this the hydrolysis of the cyanide ion. So hydrolysis of an ion is the reaction of the ion with water to produce the conjugate acid and the hydroxide ion, or it would be the conjugate base in the hydronium ion. Okay, so if this was the cation of a weak base, it would also hydrolyze. That's what this is saying right here. So the cation of a weak base would hydrolyze to form its conjugate. I'm sorry, the cation of a weak, oh, that's this one here. Okay, so the cation of a weak base would hydrolyze to form the conjugate base and the hydronium ion. Okay, now because we are increasing the hydroxide ion concentration for this particular reaction, we're going to use a KB. So remember, that's the way we're always looking at this. It's the product. So if the product is the hydroxide, then we're going to have to use the KB expression. So when we want to write the equilibrium constant expression for this reaction, again, we're going to use KB since we're increasing the hydroxide ion concentration. And so again, it's just going to be the concentration of the products, okay, raised to the power, which are all ones in this particular case, divided by the concentration of our reactants. Pure liquids and solids won't appear, so it's just going to be the concentration of the cyanide raised to the first. And so there would be our KB expression. Well, we can see the same thing. So here we have the conjugate acid of a weak base. So since it's a conjugate acid of a weak base, it will hydrolyze. It's going to give up H plus to water to form the hydronium ion and then the ammonia. And again, since these are all weak, it's going to be in equilibrium. And so all of this will exist in solution. Thus, we're increasing the hydronium ion concentration. So we're going to use a Ka. And again, it's just going to be the products each raised to the coefficient in the balanced chemical equation divided by the reactants raised to the coefficient in the balanced chemical equation. So how can we predict then whether a particular salt is going to be acidic, basic, or neutral? Well, you could, basically we know anions of weak acids, which are poor proton donors, are good proton acceptors, and thus they're going to be basic. So again, anions of weak acids are going to be basic. And conversely, cations of weak bases then are going to be acidic. Okay? So on the other hand, the anions of strong acids are good proton donors and have virtually no basic character, and that's why they don't hydrolyze, right? So for example, the chloride ion is the conjugate base of hydrochloric acid, which is a strong acid. So again, what would happen is that the H plus would transfer to form HCl and the hydroxide. But again, the HCl is immediately, since it's a strong acid, going to react with the hydroxide and go straight back to this. So again, we have the conjugate base of a strong acid and it will not hydrolyze. Again, we've seen it for sodium, the sodium ion, right? And this would be true for the lithium and the potassium and the calcium, strontium, and barium ions, right? So basically, again, we've seen that it would form sodium hydroxide, but that's a strong base and immediately would go back and dissociate. So that's not going to happen either. So again, the cations of the strong acids, so that means there's only 6 anions that won't hydrolyze. The chloride ion, the bromide ion, the iodide ion, the nitrate ion, the perchlorate ion, and the hydrogen sulfate ion. So those are the only 6 anions that won't hydrolyze. All the other anions will hydrolyze. And again, are there exceptions? Of course, but we're going to assume that they're not. Same thing here. We have the conjugate acid of a strong base. So again, we know that there's 6 cations that won't hydrolyze. The lithium, potassium, sodium, the calcium, strontium, and barium ions will not hydrolyze. So all other cations are going to hydrolyze. Okay. So how do we predict the acidity or basicity? Well, you're going to have to examine the acidity or basicity of the ions that compose the salt. So for example, we have the salt potassium acetate. So is it going to produce a basic or acidic solution? So even before you would start to quantify this problem, you should already have an idea that this solution then is going to be what? Hannah, is this going to produce a acidic solution or a basic solution? Or will it be neutral?
The the potassium ion doesn't react with the water. So it would be, I want to say acidic, but I'm not entirely positive of that.
Well, it's actually going to be basic, right? So the potassium is the conjugate acid of a strong base, so it's not going to hydrolyze. But the acetate is the conjugate base of a weak acid. So basically, it's going to react with water to pick up H plus and leave behind the OH minus, right? So again, this is the conjugate acid of a strong base, so no reaction. But the acetate ion, on the other hand, again, is the conjugate base of a weak acid. So it will pluck off, accept the proton from the water molecule to form the acetic acid, and then it leaves behind then the OH minus. Again, for these types of reactions, particularly with salts, it's oftentimes makes it easier to think of the water as being H plus and OH minus. Okay, so again, we have the conjugate base of a weak acid. It will accept a proton from water, forming a weak acid, right, the acetic acid, and so it is increasing the hydroxide ion concentration, and thus this solution will be basic. Okay, does that make sense? Okay, so basically we can apply the following rules. So for example, we have this guy here. So we see it's a sodium, and then we have this H2PO4. Well, we know that that is an acidic oxo acid. So it is not an acid by itself, but it's an acidic acid ion, right? The H2PO4 minus can still donate H pluses. So a salt of a strong base and a strong acid will have no hydrolyzable ions and therefore will not change the pH of a solution. Example, sodium chloride. Sodium is the conjugate acid of its strong base, sodium hydroxide, and the chloride ion is the weak base of the strong acid, hydrochloric acid. So these are both conjugates of strong base and strong acid, and thus it won't neither ion will hydrolyze, and so the solution is going to remain neutral. So if we have a salt of a strong base and a weak acid, well, again, the conjugate acid of the strong base is not going to react, in this case, the sodium. But the weak acid, which would be hydrocyanic acid, its conjugate base will react and hydrolyze. So it's going to, again, form a basic solution because it's going to pluck off H plus from water, leaving behind OH minus. And then a salt of a weak base and a strong acid. So again, the salt of a weak base. In this case, the weak base is going to be NH3. Remember, NH3 picks up a proton to form NH4 plus. Okay, so this is the conjugate acid of a weak base, and thus it will hydrolyze. And the strong acid, so the strong acid would have been hydrochloric acid, so its conjugate base would have been Cl. Now that's not going to hydrolyze since it's a conjugate base of a strong acid. So in this case, only this is going to donate a proton to water to increase the hydronium ion solution, and therefore the solution is going to be acidic. Okay. Okay, and then finally, the last scenario is where you would have a salt of both a weak base and a weak acid. Well, now in this case, to determine whether the solution would be acidic or basic, you would have to compare the Ka of the conjugate acid, in this case NH4, and the Kb of the conjugate base, in this case the cyanide. Whichever one of these would be bigger, well, that's going to dominate. If the Ka is bigger than the Kb, then the solution is going to be acidic. If the Kb is larger than the Ka, then the solution is going to be basic. Now, we could actually quantify this. It would be a slightly difficult problem, but we're not going to do that. Okay, so we're not going to calculate these, but know that we could. And so again, I just said this. If the Ka of the cation is larger, the solution will be acidic, and if Kb is larger, then the solution will be basic. So we could actually predict it, and we could quantify it, but we're not going to quantify it. Okay, so to calculate the pH of a salt solution is going to require the Ka of an acidic cation, so again, that's the conjugate acid, or the Kb of a basic anion, again, the conjugate base. So how do we do that? Because the tables aren't going to list the Kas or the Kbs of the conjugate acid and base. And that's because we're going to be able to easily relate the Ka and Kb of a conjugate acid-base pair. So for example, the Kb for the hypochlorite ion is going to be related to the Ka for hypochlorous acid. Again, note that this is a conjugate acid-base pair. The only difference between a conjugate acid-base pair is H+, right? So H+, if I put an H here, the plus would cancel the minus and it would give us the hypochlorous acid. So that's our conjugate acid-base pair. And when we have a conjugate acid-base pair, we're going to see that the Ka and the Kb are related to one another. So let's look at why and how. So here would be the hypochlorous acid itself, right? We would throw it in water. Proton transfer would occur. It would donate the proton to the water to form the hydronium ion, leaving behind the hypochlorite ion. For that, we'd have a Ka since we're increasing the hydronium ion or hydrogen ion concentration. But if we looked at the conjugate base, the ClO minus, the hypochlorite ion, it's going to react with water, but this time water is going to be the acid. It's going to donate a proton to the hypochlorite ion to form hypochlorous acid and thus increase the hydroxide ion concentration. Again, if we think of this as H plus OH minus, well, the H plus would go to there and would leave behind, well, we're not going to do that here, but in this case, we would, it's better to think of this as H plus and OH minus. So again, the H plus would go to there and leave behind the OH minus. Since we're increasing the hydroxide ion concentration, that would be a Kb. Now, if we add these two reactions together and we cancel what's similar on both sides, I can see that the hypochlorous is canceling, hypochlorous acid, and the hypochlorite ion is canceling. That leaves behind our two water molecules going to the hydronium plus the hydroxide. Well, we've seen this already. This is just the self-ionization of water, and we gave it a special equilibrium constant as well. We called it Kw. Now remember, when we added two reactions together from the last chapter, we multiplied their equilibrium constants together, which means that Ka times Kb is Kw. So again, now we can see that we could relate the Kas and the Kbs. This only holds for conjugate acid-base pairs, but it holds for all conjugate acid-base pairs. Okay? Okay, so let's talk about the pH of a salt solution then. So for a solution of salt in which only one ion hydrolyzes, the calculation of equilibrium composition follows that of weak acids and bases. So the only difference is first we got to obtain the Ka or Kb from either the conjugate base or the conjugate acid for the ion that actually hydrolyzes. For the one that doesn't hydrolyze, we're just going to ignore it. Nothing happens. So let's try an example. Let's say we want to know the pH of a 0.1 molar solution of lithium hypochlorite. Well, again, we can see that the lithium is the conjugate acid of a strong base, lithium hydroxide, so it's not going to hydrolyze. But the hypochlorite ion is the conjugate base of a weak acid, hypochlorous acid. So we know then it'll be the hypochlorite ion that actually hydrolyzes. So again, conjugate acid of a strong base, but this is the conjugate base of a weak acid, so it'll hydrolyze. It'll react with water. Water will donate a proton to the hypochlorite ion to form the hypochlorous acid and leave behind the hydroxide. Again, since this reaction is increasing the hydroxide ion is a product, we're going to need the Kb for it. So we're going to need the Kb for this conjugate base. We're not going to find it, right? Again, we're not going to find the Kas for anions or cations, only the neutral species. So we're going to have to look up the Ka for the hypochlorous acid. That's 2.9 times 10 to the negative 8. You just find that in the tables of chemical data or the appendix of your text. We know that Ka times Kb is equal to Kw, so we're going to rearrange the equation for Kb. So that's going to be Kw over Ka. Kw is a value that we know. That's just 1.0 times 10 to the negative 14. And the Ka, we already looked it up for hypochlorous acid. So that's going to give us a Kb then of 3.4 times 10 to the negative 7. Okay, so now we know the Kb for this reaction, so we can set up the ice table. Since this is a strong electrolyte, right, it dissociated into 1 lithium and 1 hypochlorite ion. So that means this solution is 0.1 molar in lithium and also 0.1 molar in hypochlorite. So therefore, this is going to be 0.1 molar. We'll ignore water. Again, pure liquid doesn't matter because it's not going to appear in the equilibrium constant expression. We assume that we started off with pure water before we dissolved the salt, so there would be no hypochlorous acid. And again, we would assume that we could ignore the hydroxide ion concentration from the self-ionization of water because it's such a small value. Again, we're always treating our reactions as if they're going from reactants to products. So we're going to lose our reactants. So this is a coefficient of 1, so that'll be minus 1x. We're going to gain our products, so this is going to be plus 1x. The hydroxide, we're going to gain it plus 1x. Equilibrium, just add them, so 0.1 minus x, x, and x. Again, we need the Kb expression, so Kb is going to be the concentration of the hypochlorous acid times the hydroxide, both raised to the first power, divided by the concentration of the hypochlorite ion. We'll plug in our values for Kb and our equilibrium concentrations into it. Again, I'd really rather not have to use the quadratic formula to solve this. So we're going to take our assumption where we're going to take the initial concentration divided by the Kb, and if that ratio is greater than 100, which it is, right, 2.5 times 10 to the 5th, that means we're going to be able to ignore this minus x term and just solve it by taking the square root. So we'll multiply both sides by 0.1, and then we'll take the square root of both sides to get rid of the x squared, and that gives me an x value of 1.8 times 10 to the negative 4. But remember, that x is the equilibrium concentration of the hydroxide ion, so that x is the hydroxide ion concentration. Now again, you can get the pH by either first determining the pOH and then using the fact that the pH plus pOH is equal to 14 to find the pH. Or we also know that Kw is equal to the hydrogen ion concentration times the hydroxide ion concentration. So you could find the hydrogen ion concentration that way and then take the negative log of it, okay? In this case, I'm just going to use the expression that the pH plus the pOH is equal to 14. I will rearrange it so that the pH is equal to 14 minus the pOH. Now the pOH is the negative log of the hydroxide ion concentration. So the negative log, well, that negative times the other negative will make that positive. So basically now we have the log of the hydroxide ion concentration. That gives us a pH of 10.27. Now that makes sense. Again, we would expect a pH greater than 7 if we know the solution is going to increase the hydroxide ion concentration. Any questions? So I simply want you to tell me whether the salt solution is going to be acidic, basic, or neutral. So Taylor, is the sodium perchlorate solution going to be acidic, basic, or neutral? What would you predict it's going to be?
Basic.
Basic? Okay, so we have the, first off, is the sodium hypochlorite, is it a soluble salt? Is it a strong electrolyte?
Yes.
Yeah, according to rule number 1, any salt that contains the group 1A metals are going to be soluble. So this thing would be aqueous. It's going to dissociate into the sodium ion and the hypochlorite ion. So the sodium ion, will it hydrolyze? In other words, will it react with water? And if it does, what's it going to form? If this would react with water, what would it form? Remember, you can think of water. I mean, even though it is an ionic, you could think of water, and this is best to do for salts, as being the hydrogen ion and the hydroxide ion. So what will the sodium cation react with, the hydrogen ion or the hydroxide ion?
The hydroxide.
Yeah, right. It's going to be the anion reacting with the cation to form NaOH, and then it would leave behind the hydrogen ion. Will this reaction occur?
Are you still asking me?
Yep.
Oh, yes.
Okay, what would you classify this as?
That would be a base.
Okay, strong or weak?
I think it's a weak.
Nope, it's one of the 6 strong acids, strong bases that you must know. So that means this reaction is going to go that way. So it's never going to go this way. It's only going to go this way. Okay, so this is not going to occur. Let's look at this ion. So Taylor, what will be the possible products of reacting with water with the perchlorate ion?
It would be the H2O would donate an H plus to Cl, so it'd be HCl. And an OH minus.
Yep, the OH minus would be left behind. So what would you classify this as?
I think that's a strong acid.
That is a strong acid. That's one of the 6 strong acids you must know. So will this reaction occur?
No.
No, because the strong acid is immediately again going to go that way. So this reaction would have never taken place to begin with. So will a solution of sodium perchlorate be acidic, basic, or neutral?
Would it be neutral?
Yippers. So this solution is going to be neutral. Okay. Okay, Leah, what about the this one here? What is this compound called?
Can you hear me?
I can hear you.
Okay, I think I fixed it. Zinc, that is, sorry, zinc nitrate.
So it's zinc 2 nitrate, right? It's transition metal, so you have to include those Roman numerals. So is zinc 2 nitrate a soluble or, first off, is it a salt?
It is, wait, let me think. Yeah.
Okay, so is it molecular ionic?
Okay. Ionic.
It's ionic, right? We have a metal and a polyatomic ion. Therefore, it's
Mhm.
either an acid, a hydroxide base, a metal oxide, or salt. It's not an acid. There's no H pluses here. It's not a hydroxide. There's no OHs. It's not a metal oxide. It contains metal and oxygen, but it contains another non-metal, which it cannot. Metal oxides, again, are only metals and oxygen. Therefore, it is a salt. So is this salt soluble or insoluble?
Insoluble. Wait, no.
According to rule number 2, any salt
Yeah.
that contains nitrate, perchlorate, or acetate soluble without exception. So this is aqueous.
Yes.
So that means it's a strong electrolyte, and when we throw it in water, it's going to dissociate into the zinc 2 plus ion and the nitrate ion. So is this solution going to be acidic, basic, or neutral?
It's going to be acidic.
So it will. It's going to be acidic. So let's look at why. So when I throw the zinc in, it's going to hydrolyze to form what?
It's going to form. Okay, so
It's always easier to think of water like this when we're dealing with salts.
I'm trying to think about what gains and takes away from the H. Would it be zinc? No, zinc to oxide, OH,
Hydroxide.
hydroxide. Sorry,
How many of them?
2.
2, right? So it's going to form ZnOH2.
Okay.
Okay, that means this would have to be a 2 because we're getting 1 hydroxide per water, right?
Mhm.
What else are the products?
Okay, that goes to that, and then you would plus. Oh, would this be no? Because you have the O there. Well, you have 2 hydrogen left over.
That's what's left over,
Okay, then yeah.
and therefore it would be acidic. Now, if we looked at the nitrate, again, if we think of water as being H plus and OH minus, we would expect the H plus to go to the NO3 minus, giving us HNO3, leaving behind the hydroxide. But again, this is a weak base, so it will be in equilibrium. But this is a strong acid, so it's not going to happen at all. And so therefore, we increase the hydrogen ion concentration, and this thing will be acidic. Eugenie, what about the potassium sulfide? Acidic, basic, or neutral? Okay, by the way, too, this isn't ClO4 plus, right? It's ClO4 minus. I'm sorry. This is ClO4 minus. That is the perchlorate ion.
I'm not sure.
Well, let's go through it. Is potassium sulfide a soluble or insoluble salt? Again, we recognize it's a salt because it's a metal and a non-metal. Again, you need to go, you guys, all of you guys, need to start going back and doing a lot more homework. If you thought the first exam was devastating, wait till you take this next one. And the one after that gets harder yet. So I'm telling you right now, it's going to be the same way, same length. Everything's going to be the same. What you need to do is learn the material. So is potassium
soluble.
sulfide. It's a salt, it's a metal and a non-metal. It's not an acid. There's no H's. It's not a hydroxide. No OH's. It's not a metal oxide. Doesn't contain any oxygen. Therefore, it's a salt. Is potassium sulfide soluble or insoluble?
It's insoluble.
It is soluble. According to rule number 1, with no exceptions, all group 1A metal salts and the ammonium, NH4 plus, are soluble without exception. That means this is a soluble salt and thus a strong electrolyte. So it's going to dissociate into its potassium ions in its sulfide ion. Then we have oops. Okay, then we have, we got to look at each one of these ions. So the potassium ion, again, would react with water. And what would that form, Eugenie?
KOH.
Yeah,
Plus.
again, we're thinking of water as H plus plus OH. So the OH minus will react with the K plus to form KOH. And what would it leave behind?
Hydrogen.
H plus part of it. Okay. So if this were to occur, it would be acidic. Will this occur?
No.
And why is that?
Because KOH is a strong base.
Absolutely. So this is a strong base, so it's not going to happen. So in other words, this is the cation of a strong base, and it will not hydrolyze, right?
Mhm.
That's going to be true for all the cations of the strong bases. None of them will hydrolyze, but all other cations will hydrolyze. I'm sorry, I keep sending a message to the wrong person. Michael, just ignore all the messages I've sent you. I am trying desperately to send it to Keenan. Okay. Okay, so yes, so it's not going to happen since that is the conjugate acid of a strong base. It's not going to hydrolyze. But what will the sulfide form when it reacts with water?
H2S.
And what will it leave behind?
OH minus.
How many of them?
2.
2, right? Because we needed 2 for the S2 minus, so there'll be 2, which means we use 2 waters. Now, what would you classify H2S as in water? What is it called in water? So what is this called? Just the S part, this right here.
It's sulfide.
It is sulfide. Sulfide. So when it ends in IDE and we make it an acid by adding H pluses till it's neutral, what do we do to the IDE?
Change it to IC.
Say again?
Hydrosulfuric.
Yeah, exactly. We add the hydro, then the stem. Now, in the case of sulfur, we add UR back. In the case of phosphorus, we add OR back. And then we replace the IDE with IC and add the word acid. So we had the prefix hydro, suffix ix, and added the word acid. So this is hydrosulfuric acid. Is hydrosulfuric acid a weak acid or a strong acid?
A weak acid.
It is a weak acid, which means this equilibrium will occur. And so is this solution going to be acidic, basic, or neutral?
Will it be basic?
It is going to increase the hydroxide, so this solution is going to be basic. Make sense?
Yeah.
Okay, Michael. This one here, this thing is called methylamine chloride. I will tell you that it is ionic. So is this ionic compound soluble or insoluble?
Doesn't look soluble to me.
Why is it soluble?
I said it wasn't, but I guess it is.
It wasn't? Oh, okay.
I guess
No, it is soluble. Why is it soluble? What ions are here? I'm telling you it is ionic. So what ions are here?
You got chloride, you got a NH3, you got a CH3.
Okay, no. There's actually only 2 ions here.
Okay.
What charge will either one of these ions have?
The chlorine is going to have a negative.
Yep.
Yeah.
That means this has what?
Positive.
That's right. So again, a lot of this is deduction. And it is a strong electrolyte. Why is it a strong electrolyte? What rules do you have for the methyl ammonium ion?
Well, the NH3 right there is the acceptor.
No, that's NH4 by itself. NH4, which is the ammonium ion. This is not ammonium ion. This is the methylamine ion, methyl ammonium ion. So is there any roles for methyl ammonium in the solubility rules? Nope. What about chloride? Any roles for chloride in your solubility rules?
Well, it can accept stuff.
I'm sorry?
It can accept like protons.
No, that's not the solubility rules. The solubility rules tells us whether a salt is soluble or insoluble. We need to know that to know if it's a strong electrolyte or a weak electrolyte. According to rule number 3 of our solubility rules, any salt that contains the chloride, bromide, or iodide ion, in this case the chloride, is soluble with the exception of any salt that would contain the silver, mercury, or lead. This is not silver, mercury, or lead, so this is a soluble salt, thus a strong electrolyte. Okay, and so it will fully dissociate. So now, is this solution going to be acidic, basic, or neutral? Do you recognize any ions that will not hydrolyze? Michael, do you recognize any ions that will not hydrolyze for sure?
The CH3, NH3.
Nope. So for the chloride, well, I know that's not going to hydrolyze because that's the conjugate base of a strong acid. Again, the chloride would react with water. Okay, we're thinking of the water as H plus OH minus. So that would react. So that's going to take up the H plus, right? Because we got the minus. So it'd form HCl and it'd leave behind then the OH minus. But again, I recognize this as a strong acid. And hydrolysis does not occur for the conjugates of strong acids or the conjugates of strong bases. So this is not going to occur. But then we have this reacting with water. And so again, if this is a plus, we expect it to react with the OH part of it. But in this case, this is slightly different because this is the conjugate acid of a weak base. So we're not even going to use the water in this case in this sense. So this is the difficult part. This is the Chem 112 part. The rest of this is mostly Chem 110. So now we got to recognize that this is actually the conjugate acid of a weak base, and it's going to give up H plus. So these are these neutral nitrogen containing molecules that we got to learn to recognize. That's going to form this and then give you the H3O plus. So Michael, what would you classify this as? So again, we'd have to recognize this thing is molecular. It contains nothing but nonmetals. There's no polyatomic ions. There's an NH4 plus polyatomic ion, but that is not NH4 plus. So it is molecular. But then we got to recognize that it has a nitrogen in it. And we know that nitrogen has a set of lone pairs that readily accept H plus, okay, to form the conjugate acid. So this thing would be a base, but it's not one of my 6 strong bases, so it is a weak base. So this will be in equilibrium. We have increased the hydronium ion concentration, so this solution will be acidic. Any questions with any of that? Okay, let's try another. So it says, which of the following display greater acid strength? I'm going to do that one last. I'm going to do this one next. I'm missing something. Okay, I'm missing, for some reason, a whole problem. Okay, so this, you'll just have to look at your homework. I'll read through it and write down the relevant information, but this is actually 1654. So 1654 says, what is the concentration of methylamine? Okay, so methylamine, well, let me keep reading. So methylamine in an aqueous solution that contains 0.25 molar methyl ammonium chloride. So methyl ammonium chloride looks like this. Okay. And it wants to know what is the pH of the solution. So it wants to know the concentration of methylamine. So if this is what I have in solution, right? So I have the methyl ammonium in solution. So it's ionic. The chloride ion makes it soluble. It's in water. So Jada, what are the possible products going to be?
Would it be CH3, no, CH4? And then it would be the NH3CI, Cl.
Okay. So this is why we always want to work with the net ionic equations. Okay. We're not going to jump into this. This is actually going to make it really, really difficult to solve this problem. Okay. So let's forget about this part of it. We've already established from the last problem, we just did the methyl ammonium chloride, right? So we just established that it is a strong electrolyte and it dissociates into the methyl ammonium ion and the chloride ion. So we're talking about pHs and concentrations of methylamine. So can I ignore either one of these ions? Remember, we're looking for the pH of this solution as part of it. We're looking for the pH. So that means we're looking for hydrolysis. Will either one of these ions not hydrolyze? So again, that's what we just did. That was this last problem.
Okay.
Right? So again, we said that the chloride isn't going to hydrolyze because it would form HCl. But the methylammonium ion will hydrolyze to form this, which is the methylamine, and H3O plus. So again, we know this is not going to hydrolyze. It's the conjugate base of a strong acid. Conjugate bases of strong acids don't hydrolyze, and conjugate acids of strong bases don't hydrolyze. So that doesn't hydrolyze. So what we're really looking at is this. So it's this reaction right here that we just discussed, right? It's going to donate a proton to the water. So it's going to form CH3NH2. Again, it's going to be aqueous. It's a neutral water molecule. It's a neutral molecule, but it has the same intermolecular forces, hydrogen bonding, dipole-dipole interactions, and London forces. So it'll be completely soluble in water, even though it's neutral. And it would leave behind the H3O plus, which is our acid, right? That's the hydrogen ion or hydronium ion. So that's our acid. So this solution is going to be acidic. So again, the question asked, what is the concentration of methylamine? And it told you that this thing was called methylammonium chloride, okay? So this is our, oops, that's a YL. Oh, forget it, let's start over. So when we deal with these nitrogen-containing molecules, they are usually amines, which end in INE. So for the amines, so these are amines, the INE goes to IUM when they ionize. Okay, so that means if this is methyl ammonium, well, the methylammonium ion goes to the methylamine. So this is our methylamine. So part of the question is asking, what is the concentration of methylamine? Okay, so there's our question. We want the, what is the concentration of methylamine, and we want the pH. So Hannah, how am I going to go about answering? Let's start with the concentration of methylamine. Big picture, what am I solving for? What am I looking for?
So the concentration of methylamine can be found by using the concentration of the methylammonium chloride, because it's a 1-to-1 molar ratio. So the
Okay, so you're saying that this dissociates, right? If this was 0.25 molar,
right,
that means that both of these are going to be 0.25 molar and 0.25 molar. Okay, I
right,
agree with you there. So we know that the concentration of this then is 0.25 molar. But I want this. How much, big picture, how am I going to get this? The methylamine itself, the neutral. I just want you to step back and think about how you're going to solve this problem overall.
generally through ice tables.
Okay, so if I'm setting up an ice table, what in this ice table is going to help me answer that question?
Well, I'm looking at it and I'm thinking that everything is at a 1-to-1 ratio. So it's you have the starting value of the methylamine.
This is methylamine.
Well, okay.
This is methylammonium.
So the starting value of the methylammonium.
Okay, and that is what?
The 0.25.
Okay. Okay, so let's just go through them and finish the table. What's this going to be then?
0.
0. We assume pure water.
Mm-hmm.
And the hydronium?
Negate the hydrolyzation of water. Hydrolysis of water, so 0 as well.
Right. We're gonna the hydrolysis of water, or the self-ionization of water, is so small that we'll just assume it's 0. Okay, the change in the methylammonium ion.
Negative X.
Yep. So we're going to lose our reactants, and then the change in the methylamine.
Positive X.
Plus X. And the hydronium ion?
Positive X.
Okay. At equilibrium.
0.25 minus X.
Yep. We're just adding up the initial and the change. So 0 plus X is X. 0 plus X is X. Okay. So coming back to this question, where am I going to get this number from? How am I going to get this number? So you set up your ice table. Where am I going to get this value from that ice table?
The tables of chemical data. Would that?
You're giving me details. I want to know where I'm going to get this concentration. With what you gave me so far, you could answer that question.
It's going to be equal to the concentration of hydronium ions. So.
Okay, or it's just X, right? X is the concentration of methylamine, right? This is the equilibrium concentration of methylamine. So we're just looking for X. Okay, so now how are we going to get X?
Is that through the use of the tables of chemical data in that case?
Okay. So we're going to need an equilibrium constant expression. So what's that going to look like?
The concentrations of the methylamine and hydroxide over the concentration of the methylammonium.
Okay, I agree with you. And what does that equal?
I want to say it's either the Ka or the Kb value, but I can't.
Okay, so that's the question now. Remember, I said this is really easy. How do you determine what you use, Ka or Kb? It's really easy to determine whether you use the Ka or the Kb.
What I think it's what's left produced, so it would be the Ka value.
Right. We increase the hydronium ion concentration, so it's going to be Ka. If the product was hydroxide, then we would use the Kb. Okay. Okay, so now we could plug, well, wait a minute. What is the Ka? Where am I going to get that value?
You can't, I don't think you can get it directly.
We can't, because we generally can't get the Kas or Kbs for ions. So this is the conjugate acid of what base?
I forget what it's called, but I know what I'm looking for.
What's the difference between a conjugate acid and a conjugate base?
The presence of hydroxide.
No.
No.
What is the difference between a conjugate acid and a conjugate base? Again, very simple. What is the difference between a conjugate acid and a conjugate base? Anybody?
The proton, I like the H.
Yeah, H plus, right? So if this is the acid, we're going to take away H plus, which gives me methylammonium, or I'm sorry, methylamine. So methylamine then would be our conjugate base. So we're going to look up the Kb for a base. And so the Kb for methylamine, when you look it up in a table, is 4.4 times 10 to the negative 4. Okay. So now how's that help me get the Ka? So Taylor, how's that going to help me get the Ka?
Like the Ka and Kb are related somehow, but I forget.
Anybody want to help her out?
Would you use the KW somehow, like
Yep.
A divided by KW equals KB?
Yeah, right. Again, we know since these are acid-base conjugate pairs, the only difference is H plus. And again, only in that situation, when we have an acid-base conjugate pair, Ka times Kb is equal to Kw. So if we know Kb and we know Kw, that's the number that you must memorize, then we can rearrange it and find Ka. So Ka is simply going to be equal to Kw divided by Kb, which is 1.0 times 10 to the negative 14 divided by the Kb that we just looked up, 4.4 times 10 to the negative 4. And so that's going to give us a Ka value of 2.272 times 10 to the negative 11. Okay. Is everybody good with that? Okay, so now we know Ka. So Ka is 2.272 times 10 to the negative 11. The concentration of the methylamine is X. The concentration of the hydronium is X. X times X is X squared. The concentration of the methylammonium ion is 0.25 minus X. Again, I do not want to have to solve the quadratic formula. So I'm going to take Ca, right, since this is Ka. So Ca over Ka. Ca is our 0.25. Ka we just determined is 2.27 times 10 to the negative 11. Okay. Plug that into your calculator and you get a value of 1.1 times 10 to the 10, so 11 billion. That's definitely greater than 100. That's going to allow us to ignore that minus X term. So now we have X squared is equal to 2.27 times 10 to the negative 11. We'll multiply both sides by 0.27. We'll then take the square root of both sides to get rid of the X squared part. So X then is just going to be 2.3836 times 10 to the negative 6. So the first part simply asks, what is the concentration of the methylamine? Well, that is X. So the concentration of methylamine is equal to, now this only has 2 sig figs, so this is going to be 2.4 times 10 to the negative 6 molar. So that would be the concentration of methylamine. Then it wanted to know, what is the pH? Well, the pH is just the negative log of the hydronium ion or hydrogen ion concentration. Well, that's also X. So this is also equal to the hydronium ion concentration. And therefore, the pH is just the negative log of the hydronium ion concentration. So that's just equal to the negative log of the 2.3 and that is going to give us a value of 5.622. This log value is to 2 sig figs, so this will be to 2 decimal places, so 5.62. And then as a quick check to yourself, well, I know that it's going to become more acidic, which means I should have a pH that's less than 7, and I do, so I probably did everything right. Any questions? Okay, let's try one last one. This is number 66. It says, list the following in order of increasing acid strength, so weakest to strongest, right? So this will be weakest to strongest, based on the respective ionization constants. So in other words, the K values, And so we're talking about acids, we must be talking about the Ka values. So we got ammonium bromide. And I need the Ka value for ammonium bromide. So the Ka value. Would you classify this as an acid, base, or salt? Anna, what do you think? Ammonium bromide, is it an acid, base, or salt?
I think it's a salt.
Okay, so it's ionic, right? It contains a polyatomic ion and another nonmetal, which will be the anion. It has no H's out front, so we don't recognize it immediately as an acid. That doesn't mean it isn't. We could look it up and see if this has a Ka value. It doesn't. So you would look it up and you'd find that it has no Ka value. There's no hydroxide, so it can't be a hydroxide. It can't be a metal hydroxide. It doesn't have metal or oxygen, therefore it's a salt. Is this salt a strong or weak electrolyte?
It's strong because of the presence of ammonia.
Yeah, right. The rule number 1 says that any salt that contains the group 1A metals or the ammonium ion is going to be soluble without exception. And for salts, soluble means that it is a strong electrolyte, so it's going to dissociate into the ammonium ion and the bromide ion. Well, for this thing, for these ions to have a Ka value associated with it, means that the ions must hydrolyze. They must react with water. Will either one of these ions not hydrolyze?
Bromide won't.
Yeah, right. The bromide is the conjugate base of a strong acid. And again, conjugate bases of strong acids. So again, you know your 6 strong acids. So the counter ions of those 6 strong acids, bromide, chloride, iodide, nitrate, perchlorate, and the hydrogen sulfate ion will never hydrolyze. And again, the same thing would be true for the conjugates of your strong bases. So the lithium, sodium, potassium ion, calcium, strontium, and barium ions, those 6 ions will never hydrolyze. So you know of 12 ions that will never hydrolyze, but the rest will. So that means this is not a conjugate of a strong acid or a base. In this case, it's the acid, so it's not the conjugate of a strong base. So we know that it will hydrolyze. So when when NH4 hydrolyzes, again, that means react with water. And what will be the products?
NH3 plus hydronium.
Exactly right. So we're going to have a proton transfer reaction, which is going to leave behind. We're going to take H plus away from this, which gives me NH3. And then we're going to give the H plus to that, so H3O. So yeah, it is acting like an acid, right? It's increasing the hydronium ion concentration. Okay, but we know that it's actually the NH4 part of this that's acting like the acid. So how are we going to determine the Ka? So I need the Ka of NH4. How am I going to get that?
In a table, in the list, like a list of tables that you gave us.
Okay, so specifically, what am I looking up in that table? So I can't find the Ka of NH4 by looking it up in the table. So what am I going to look up? NH4 plus is not in any of those tables.
You look up
Base.
base.
I'm sorry, say it again.
I
Look
said
up.
base.
Look up the Kb of what?
NH3.
Yeah, right, it's conjugate base. So if this is the acid, this is the conjugate base. So I'm going to look up the Kb of NH3. So I look it up And the KB of NH3 is 1.76 times 10 to the negative fifth. So how's that help me get the Ka, Eugenie?
Divide Kw by the Kb.
Yeah, again, we know that Ka times Kb of a conjugate acid-base pair is equal to Kw. So I'm just going to rearrange this equation for Ka. So that means that's just Kw over Kb. So that's the 1.0 times 10 to the negative 14 divided by our Kb that we just looked up. 1.76 times 10 to the negative fifth. And that is going to give us then a Kb value of, a Ka value of 5.68 times 10 to the negative 10. So this is 5.68 times 10 to the negative 10. Okay, next we have nitrous acid, so HNO2. And how am I going to get the Ka for that? What would I do? What is that called? What is that called? HNO2 in water. What is that called? What would you classify it as? Molecular ionic. Lee, is this thing molecular ionic?
It's I'm sorry. Yeah, molecular. Right?
Are there any recognizable polyatomic ions in that formula? You all must. Keenan.
Oh, okay. Nitrate?
The not nitrate.
Wait. Nitrite.
Nitrite, right? NO2, NO minus is nitrite. So what is HNO2 in water then? So it's ionic. So is it an acid or a base? Acid, hydroxide, base, metal oxide, or salt?
Acid.
Yeah, it has the H out front, so it must be an acid. So if this is nitrite, what is this called in water?
Nitrous acid.
Nitrous acid.
Yeah.
Okay, so how am I going to get the Ka? How am I going to get its Ka? Taylor, what do you think? How am I going to get the Ka? For nitrous acid.
Did you say Taylor?
Yep.
Oh, since it's an acid, would you just look it up and
Yeah.
make it a table?
Exactly right. It's already an acid. So I'm just going to look up the Ka value in the table, right? The acids are already going to be listed. So that's nitrous acid. I'm going to look it up in a table. And nitrous acid has a Ka of 4.6 times 10 to the negative 4. Let's see. Next, I have hydrozinium chloride. So Taylor, what would you classify that as? Is it molecular or ionic?
Molecular.
One way to figure out, okay, if it's not, is let's just look at it real quick, right? We have a nitrogen. A nitrogen has a lone pair and 3 sets of bonds. Most likely this nitrogen, since it's written like that, is connected to this nitrogen, which has 1, 2, 3 bonds and a set of lone pair. The hydrogens all have a single bond. Wait a minute, but that is now all of them, but yet I have another hydrogen which probably did this, and that would have been as an H plus, leaving this behind. So by drawing the Lewis dot structures, you could tell that there was no way for me to draw a Lewis dot structure with these nonmetals, because I know, again, going across the periodic table, where's my periodic table? For these guys here, since they can't violate the octet rule, carbon being in group 4 can make 4 bonds, whether they be 4 singles, a double and 2 singles, 2 doubles, a triple and a single, but 4 bonds. Nitrogen having 5 valence electrons, 1, 2, 3, 4, 5, can form 3 bonds and have a lone pair. Oxygen being in group 6, 1, 2, 3, 4, 5, 6, can form 2 bonds, whether it be 2 singles or a double, and have 2 sets of lone pair. And then the halogens have 7, 1, 2, 3, 4, 5, 6, 7. So we can see the halogens generally only form a single bond. So by using this idea to draw my Lewis dot structures, I can draw a Lewis dot structure literally in seconds for any molecule, okay? So again, that's how we got to this idea, that there was no way that all these nonmetal atoms could possibly make a probable Lewis dot structure without violating the octet rule. So that gave me a clue that this wasn't. The other clue, of course, was its name, hydrazinium chloride, right? If this was molecular, it would have been called dinitrogen pentahydrogen chloride, monochloride. Well, we didn't see that in its name. Its name indicated that it was ionic. Okay, so you see all the clues of being able to see whether these things are molecular ionic. I almost always give you the name with these weird ones. I always give you the names with the weird ones. Okay, so this thing is ionic. So if it's ionic, right, so if this thing is ionic, it's obviously not an acid. There's no H's out here. Okay, it's not a hydroxide base. There's no OHs. It's not a metal oxide, doesn't contain metal or oxygen. Therefore, it's a salt. So is this a soluble salt or an insoluble salt? Jade, is this going to be a soluble or an insoluble salt?
It's going to be insoluble.
Insoluble? Do you agree, Leah?
Because of the,
I'm sorry?
isn't it because, no,
I just can't hear what you're saying.
I said it's going to be insoluble.
Insoluble. Okay, Leah, do you agree? No, why not? So you're saying it's soluble.
Yeah.
Why? What's this thing? If this could dissociate, what would it dissociate into? Again, knowing this is the name of it.
And to put,
We know that's plus because the chloride would be 1 minus. Plus, we just seen it when we drew the structure of it.
yeah, so it's soluble. Right?
Any role, so why is it soluble?
Well, isn't, okay, I forget the real number, but chloride.
Yeah, I don't care that you know the rule numbers.
Okay.
Rule number 3, and it says that any salt that contains a chloride, bromide, or iodide is soluble with the exception of silver, mercury, and lead. That isn't silver, mercury, or lead ions. So that means this thing is soluble. So it is a strong electrolyte. It's not a double arrow, it's a single arrow. It simply dissociates into these two things. Now, again, we're trying to compare acids. which one of these would we consider to be an acid?
The N2, H2, H5.
Yeah, this here, right? This is going to be the conjugate acid of a weak base. So if this is the name of this, right? This is hydrazinium. What do you think the base is called? Right? Because this is going to act now as an acid. It's going to react with water. It's going to donate a proton. It's going to form N2H4 plus H3O plus. Now, you don't need to know the name, right? Because you know this is the acid and this is the conjugate base. So all you have to do is look for this formula and look for the KB. But they're listed in alphabetical order. So I know it's going to be hydrazine something. But remember, we replaced the IUM with INE. So I'm just looking for hydrazine. So I'm going to look up the KB for hydrazine. The KB for hydrazine is 1.3 times 10 to the negative 6. Again, I'm going to use that idea of Ka times Kb equals Kw. So Ka is just Kw over Kb. So that's 1.0 times 10 to the negative 14 divided by the Kb of 1.3 times 10 to the negative 6. That'll give us a Ka of 7.7 times 10 to the negative 9. So that means the hydrazinium chloride, it's the hydrazinium part acting as the acid, has a Ka of 7.7 times 10 to the negative 9. Okay, any questions about that guy? Okay, let's go with the next one. So hydrozoic acid, HN3. So we got hydrozoic acid. So Taylor, what am I going to do? I'm looking for Kas.
It's an acid, so just look it up in the table.
Yeah, it's hydrozoic acid. So let's just look it up in the table. And when I look up hydrozoic acid, it has a Ka of 2.5 times 10 to the negative 5. And then finally, I have aniline nitrate. Who wants to tackle it? The more you practice this, the more you learn.
So the aniline nitrate would break down because it's aqueous.
And form what?
Because of the nitrate.
No, I agree with you, but to form what?
The aniline and nitrate.
Okay, so this thing here, and it's going to have a +1 charge since that has a -1 charge. Will the nitrate hydrolyze?
No, because it would form the strong acid.
Right, it's the conjugate base of a strong acid, so it's not going to hydrolyze. So what we're interested in is this guy here. This guy here, of course, is going to hydrolyze. We can see that it's actually going to donate a proton and form this plus our acid. So again, it is going to be acid. We're going to have a Ka value associated with it.
Okay.
So what am I going to look up the Kb value for? So again, we're going to do the same idea. Since this isn't directly an acid, it's got to be the Kw over Kb. And so what are we going to look up for the Kb? Either give me the name or the formula. What am I looking for the KB?
aniline, aniline.
Yeah, right. So again, if this is anilinium, well, we're probably going to replace the IUM with INE, okay? Or simply look up this, right? Look for the KB for this formula, okay? So this is the anilinium ion. So this would be anilinium. It's hard to pronounce, okay? But I'm going to look up the KB for this, and that is going to be 3.9 times 10 to the negative 10. Plug that into your calculator, and you're going to get 2.6 times 10 to the negative 5. So now we have our anilinium nitrate, so C6H5NH3NO3. Again, known it's the anilinium ion that's acting as the acid, and we just calculated its Ka to be 2.6 times 10 to the negative 5. Okay, so everybody gets that portion of this problem. We had to go through and find the Kas. Again, on the exam, I would expect you to be able to do this in 5 minutes at the most, even though we just spend half an hour on it. Because you got to recognize immediately of what type of compound it is. You got to recognize that was a salt, an acid, a salt, an acid, a salt. Sometimes the name gives it away. Okay? Otherwise, you got to recognize that it's ionic, which again, the name will give that away. Even though this contains nothing but nonmetals, this is named as an ionic compound, not as a molecular compound, as I stressed over and over and over in Chem 110. The better you know how to name your compounds, the easier Chem 112 is going to be. And by the end of Chem 112, if you still don't know how to name your compounds, I guarantee you'll be taking Chem 112 again. Okay, so again, there we go. So now we know then that this is the conjugate acid of the base. So I don't need to go through all this. I could do this in my head. I look at this and I say, okay, well, that's a salt. That is the conjugate of a strong acid, so it's not going to hydrolyze, but this is not. So that means that's acting as an acid, and I know the conjugate base, all I got to do is take H plus away. So that's going to become N2H4. Now I just look up the Kb for N2H4 and take Kw divided by Kb to give me my Ka. So that should be the thought process, and that took all of 2 seconds. Okay, that comes with doing your homework. Okay, so now I want to go from weakest to strongest. So what am I looking for? Which one's going to indicate that I have the weakest acid? What's going to indicate my acid strength in this case? If I have something that's acting like an acid, it could either be like this, right, which generally is, and it's going to go like this. This being an acid, how would a K value, an equilibrium value, indicate whether we have a stronger acid or a weaker acid?
It'd be the stronger the K value, the stronger the acid is, because the more products there are, the higher the...
Exactly, right? This is all going back to chapter 15. Chapter 15, we know the larger the K value, the more products, which means the more H plus, which means the more acidic. So the strongest acid is going to have the largest K value. The weakest acid is going to have the smallest K value. So which one is the weakest acid then?
Ammonium bromide?
Yeah, the ammonium bromide, right? It has the smallest Ka value. So it would be NH4Br. What's going to be next?
Hydro,
Good.
hydrozinium chloride.
Okay, so that's this one here, right? 10 to the negative 9. So hydrozinium chloride, followed by now be careful. Think about it. Do you want the smaller value or the larger value?
Hydrozoic acid.
So you're saying this one's weaker than this one. 2.5 is less than 2.6. These two acids are almost identical in strength, but this is a slightly weaker, right? 2.5 is smaller than 2.6. So it's going to go the hydrozoic acid. And then finally, we're going to get to the aniline nitrate. Whoops, what am I doing? And then finally, the largest, right, 10 to the negative 4 is 6 times larger than 10 to the negative 10, right? So it's going to be the nitrous acid will be the strongest of them all. Okay, any questions about that stuff?